Please take the stand.
So, good morning. My name is VII Carot. I'm a professor at the University of Applied Sciences, Hochschule Anhalt in Germany. And I may introduce myself a little bit further because there is a big difference between me and Günther Nims. And actually, I'm not a physicist. I'm a computer engineer. So I do computer science, especially media computer science. So I'm working in a different field. So I'm more interested in the application of physical aspects. And this is what I'm talking about. And I'm hoping to lift the whole discussion to a more practical level. And I actually think that many questions which are not really answered might be answered within my talk. At least I'm hoping that this will be the case. So I'm talking about the application of faster than light in information technology and in media communication. And first of all, I would like to introduce into the topic, and I would like to describe my motivation, why I'm working in this field. And the thing is, I'm a musician. And this motivation I'm a bass player, by the way, of playing with somebody who's not in the same room is something that drives me for more than 10 years. And this is the idea. You have two instruments playing together in the same room. And my idea is to, if you have two rooms in the world, to connect these two rooms where the instruments, where the players are, and connect them via the internet. This is something I have been working on for the last 10 years, and develop a system that transmits the signal so fast that the players don't actually perceive the latency. There is a latency between the players, but it is so small that it is neglectable in terms of musical interaction. And if we have such a scenario and two musicians are connected via a communication path, we have many stages. And in fact, I do a lot of digital signal processing. And just let me go quickly through these stages. There is not enough time to explain all of these stages, but you have one very significant part in that signal chain, and this is here. It is where the routing happens, so where the actual signal transmission happens. This is here the backbone path of the internet, for example. So we have, it looks like a subway metro plan, and in this particular case, or in the current situation, the signal or the IP packet, the internet packet, travels with 70% of the speed of light. That's what the propagation delay in fiber optic lines is. And if we have a propagation delay of actually 200 of propagation speed in the fiber optic domain, it is 230,000 kilometers per second, and then we are able to obtain 28 milliseconds within approximately 2,000 kilometers. The problem is, if we want to interact musically on long distances, we have to remain below 25 milliseconds. So this is my overall goal. So I have developed a system that is able to do that. It is based on the internet, but I have the big problem that this is the upper limit I can go with. So an international music jam session, for example, between Europe and the United States is not possible at all because the distance is too large because of the speed of light. So this is my motivation, and this is where I try to revisit Günther Nims' experiments to find a solution which is able to transmit my signal faster than the speed of light in order to obtain international music sessions. So that's the idea. And this is Günther Nims, as you saw him previously, and with the double prism experiment. And you see the distance between these two prisms in which he was able to achieve superluminal speeds is several centimeters long. And this is something, of course, something I cannot work with because it's way too small. I want to achieve 10,000s and more of kilometers, so I want to have a global, I want to have a worldwide connection, a worldwide superluminal connection. So, and this is the motivation, this is what I want to achieve. I want to lift the experiment from from low distance to long distance signal tunneling. That's the overall idea, that's my motivation. And as he explained already, that's the theory behind. We have a wave packet that approaches from the left to the right towards a barrier. Most of the signal is actually reflected because it can't get through the barrier. But a damped part of the signal is able to travel through the barrier, and it does that in 0 time. Believe it or not, we measured it, and I will show you later. Here's at least a 50-meter superluminal path, which I will present later, but this is what is actually happening. Again, the double prism experiment, that's the normal case where the signal propagates through the prism, and now we shift the 2 prisms apart, and the D is several centimeters long, but the D is not measurable. The time we measure here is equal to the time we measure here. So that means that the time spent within the gap is 0. That is the most descriptive way how to describe the tunneling process, in my opinion. And again, another sketch of it. And again, the real photon, and within the gap, the virtual photon, which is not measurable. And when it comes out, again, the real photon. This is what we can measure. As I mentioned, the most descriptive way to explain tunneling is here the double prism, but we have 2 other ways. Actually, we have a 4th one, which we might cover later on. But this is the undersized waveguide principle. So we send the signal through this one, and we want to receive it here. But within the 2 waveguides, we have a smaller waveguide. And this waveguide is, in that sense, smaller, that the passable wavelength is in fact smaller, so the incoming wave is reflected because the wavelength doesn't fit into the smaller waveguide. So we have one waveguide here, the undersized waveguide, and the normal waveguide on the receiving side as well, and this is the tunneling barrier. And the third principle is a grating, and this grating has the same effect because it simply reflects the incoming wave. And either way, if we use the grating, the undersized waveguide, or the double prism, this is the principle. This is the frequency that is able to pass the barrier. And here we have the conventional propagation with the speed of light. But once the frequency decreases, so in lower frequency regions, the signal can't pass the barrier anymore. And this is the part where we observe superluminal speeds. This is where we have a damped signal of approximately 30, 40 dB, or even more. Within that range, we discover superluminal propagation. And here we see the spectrum of the grating. That is the experiment done on the glass fiber by Longhi approximately 10 years ago. And he used exactly that so-called forbidden range. And within that forbidden range, he put a pulse and transmitted that pulse. He also put another pulse besides the forbidden range, and he compared these 2 pulses regarding the latency. And what you can see clearly is that the pulse transmitted within the forbidden range is shifted to the left, so it is earlier than any other signal that is sent in other ways. So that was the theory, which I kind of repeated. And now, what's my goal? My goal is to exceed the physical distance from several centimeters to meters or more in order to finally achieve a worldwide, whenever that might happen, I don't know, network. He measured time shift of several picoseconds, so I'm approaching nanoseconds or microseconds to make it more obvious. And I also want to do that in order to show that this is not a measurement fault. So I simply want to see that this is a proportional relation in terms of tunneling. And furthermore, in order to move away from theoretical discussions and interpretations, I want to have clearly audible results. I want to have something we can clearly judge in terms of seeing or hearing any real signal. So I want to actually lift it up, bring it away from theoretical interpretations. I want to bring it into the real world, so to speak. This is my goal. But as usual in science, I have a problem, and this problem is the damping of the signal. So the problem is that if we have a conductor that considers this as an undersized waveguide, the problem is that if we put the signal in here and we take it out here, the signal strength decreases exponentially. And that means on 1 meter waveguide, undersized waveguide, for example, we have already a damped signal of 70 dB. And 70 dB is almost nothing. And imagine 2 meters more, we end up with something with signal strength we cannot work at all anymore. That's the main problem with the classical tunneling process. However, there's an alternative. What we can do, we use this 1 meter as a normal, not tunneling waveguide. So this is the waveguide that is able to transmit the signal in the conventional way. But we put 2 tiny waveguides, one at the beginning and one at the end of the waveguide. So we kind of divide the tunneling barrier and put one on the front and one at the end of that. In that setup, we have a small damping, and we can still have a long transmission path. But the problem is that now the spectrum looks different. Now the spectrum is disturbed, so to speak, by these peaks. So we have, in a certain delta F, we have transmission in the conventional way. And this is a so-called Fabry-Perot behavior, and this has so-called maxima and minima. In the minimum, we still have the behavior as described previously with superluminal speeds, but within the maximum, we have conventional signal transmission and even slower. That means I can put my signal here, but if, in terms of frequency, it increases, or if it's too large, it will finally fall into these, and then it will be disturbed. It will be distorted, and we won't notice, or we will see problematic superluminal behavior, which is not the overall goal. And the next problem is, the longer we exceed that distance, the tinier the delta F. So the longer the tunneling distance, the smaller the signal bandwidth we can actually use for this specific topic. Yeah, and this is just an example. 1 kilometer, so if I had a waveguide of 1 kilometer, I would not be able to use a signal that has a bandwidth of more than 105 kilohertz. This is very small. It's still something beyond our audible range, but this is probably something we can work with, because in terms of digital signals, we need very steep slopes, so we need rectangular pulses, and we are not able to form a rectangular pulse with high bandwidth if we have only 105 kilohertz available. That's the main problem. So I simply accept these preconditions, and here's my concept. Again, we have a barrier, so an undersized waveguide. we split this barrier into two barriers, and we use our conventional conductor in between. But the problem is what we have to live with these Fabry-Perot behavior within the medium. And this is where the bandwidth problem comes from. And this is something I've done previously. So this is not this experiment. This is the forerunner of this experiment. I decided to use a conductor length of 20 meters. So I have my signal generator that generates a sine, a single sine of, no, it's actually a continuous sine of 500 kilohertz. The output is AM modulated with a carrier frequency of 9 gigahertz, because this is the frequency the whole setup is made for. So it's in the microwave domain. Then I have a 2 centimeter Ku band waveguide tunnel at the beginning of the 20-meter path. Then I have 20 meters, and at the end of the 20 meters, I have again a 2 centimeter smaller waveguide. Then the signal is demodulated, so I push away the carrier, and I display the sign on the oscilloscope. In parallel, I do that on another waveguide, which has no tunneling Ku band pieces at the beginning and at the end. So this is the conventional path, and this is the tunnel path. And on a 2-channel oscilloscope, I can measure a clear time shift, or I intend to measure a clear time shift. And since 20 meters is quite long, it doesn't fit into my office, I decided to use a tube and coil it up. And that was the first try, and it was actually quite high. So I'm feeding the signal here into the waveguide. Here's the small Ku band piece, and it moves all the way up. And there I have the output tunnel, and there I grab the signal and feed it to the oscilloscope. And regarding your question in terms of polarization, I have to point out, just for the sake of completeness, that the input is a rectangular waveguide. But since I have this copper tube, I have an adapter, and this adapter changes the linearly polarized wave to a circular wave. But just for the sake of completeness, but that doesn't really change anything regarding the tunneling principle. So I have my carrier of 9.15 gigahertz, and I modulate a sine on top of it, and that implies it's an AM modulation, that I have a lower sideband, I have an upper sideband. So these here, the bandwidth is altogether 1 megahertz. So I have 500 kilohertz towards the lower sideband, and I have 500 kilohertz towards the upper sideband. And here are the results. This is what I measured with a Rode and Schwarz network analyzer. I mentioned that because it's a very expensive and very good tool to see how the signal behaves over frequency. And what's interesting, without the tunneling pieces, I have a flat transmission, and the signal is damped by approximately 3.5 dB. That is the natural damping because of the 20-meter waveguide. And if I put the tunneling pieces, as described previously, one on top and one at the beginning, I see an altogether clearly damped signal, and as I described, it vibrates in that Fabry-Perot behavior which I described with the specific minima and the maxima, and minima, maxima. And it does that in clear shifts of 5 megahertz. And this is what you can actually calculate. It's a very clear calculation, and it kind of predicts that kind of behavior because there is a standing wave within the medium. and that is responsible for that kind of behavior. And what I did, of course, I used the minimum and not the maximum, and here I expect superluminal propagation to happen. Also, for the sake of completeness, this is the phase of the signal. I measured that as well. The gray one is the conventional transmission without the tunneling pieces. And this is also a very, very typical way to describe that. And in the tunneling experiment, we see these parts here. And within these parts, we have that kind of phase. And that kind of phase, by theory, implies that there must be zero time within the medium. So this is already what the network analyzer shows me. And again, for the sake of completeness, that everybody understands what I'm doing, I have the carrier frequency, I have the lower sideband, I have the upper sideband, and I just make sure that this is really within the minimum of the transmission. This is happening at 9.15 gigahertz. Just to point out, if I was using a higher carrier here, I would not observe that desired transmission. And the next problem, if I use a slightly higher frequency, I would have signal distortion because, by the way, because that behavior also corresponds to the group delay. I'm not showing that in that presentation, but if the scale would not be the magnitude, if the scale was the group delay, it would indicate, and this is what the analyzer really tells, 0 seconds, and it would here tell 100 nanoseconds, because this is what directly corresponds to 20-meter regular with the speed of light transmission. And now it's getting interesting. On the left is the input signal. So before the transmission, this is what we have directly, if we put the two adapters together, so if there was no transmission path in between, so there's what we could also call the shortcut, but I don't want to confuse you. So there is no conductor in between, and this is the direct measurement from in to output. And this is the left one, the left sign. On the right one, if we transmit conventionally, so we don't use tunneling pieces, we transmit the signal in a conventional way, and then we measure a time shift of 100 nanoseconds. And this is directly what corresponds to the speed of light, actually 70% to the speed of light because of the refractive index of copper. And so this is what is clearly, and this is what everybody would underline as correct. This is what has been measured for ages. And now, and this is the next slide, I will show you what is happening when I use the tunneling pieces. And that's it. But now, the left one is not the shortcut anymore. Now, the left one, oops, 1 second. Yeah. Now, the left one is the signal that I transmitted on the 20-meter copper waveguide with the tunneling pieces. And if you see, if you compare, there is no difference between. So the left, in the first measurement, the left one is the shortcut, so no conductor in between. And in this measurement, the left one, the fast one, is the one that I transmitted on 20-meter copper waveguide. So that essentially means that the tunneling signal is transmitted in 0 time because it 100% overlaps with the shortcut. And then there is, of course, again, a 100 nanosecond gap in comparison to the conventionally transmitted signal. And my conclusions are that I have to confirm NIM's observations, and I did that on a distance of 20 meters, which is approximately factor 1,000 of what he has done previously. I have to admit, I have to say that these time shifts are still far away from being audible, so this is just something we can see on the oscilloscope. It appears, or it is, at least for me, it's quite clear that this instantaneous transmission is possible. However, as I mentioned, with increasing conductor lengths, the available signal decreases proportionally. So we have more an engineering problem if we want to if we want to use this principle in terms of digital networks, for example. Nevertheless, and I'm interested in audio, I could be able to cover a distance of 1 kilometer, and then I could apply one more tunnel and so forth if I had somebody who would pay this experiment. So that would theoretically be possible, and then I could be able to achieve longer distances. But that would apply to, they would assume to have, of course, more than one tunnel. And this is the main problem. Digital signals with rectangular shapes are problematic. And for those of you who don't know what I'm talking about, this is what I consider the available bandwidth within the minimum. But if we have a more complex signal, like a rectangular pulse, we don't have only one carrier and we have one single sign spectral line on the left, on the right. We have more harmonics to the left and the right. And if these harmonics fall out of the gap, fall out of the available bandwidth, the signal at the end is either distorted or, and this is rather more problematic, it is not transmitted with the speed of light because it already falls into the maximum, and the maximum is even slower than the speed of light. I don't want to go too deep into the details of that picture, but this is something where I have actually done that. So here I'm not using a single sign anymore. Here I'm using a signal that starts from 0, it shows 2 vibrations, and then it falls back to 0. The right one, as you see, is transmitted properly, so there is no problem in that sense. And the left one I tunneled. And here is where the problem starts. You see that both signals start at the same time because the left one is not transmittable within that small frequency range. This is why the superluminal propagation starts later. It starts at that part. Once it is vibrating, we don't have such a problem. But again, when it falls back to 0, you can see that the tunnel signal is not immediately shifted to 0. There's another vibration. This is also because of the limited bandwidth, and this is because of the engineering problem we have. Yeah, as I cleared out here. So again, oops, with single signs, it's not that problematic, but if we have pulses which start from 0 and have to be back to 0. So this implies higher frequencies. And if we are not able to keep these frequencies within the allowable frequency range, we have problems. We have signal distortions. And by the way, regarding your question concerning the front velocity, this is directly related. But the thing is, the front velocity implies unlimited frequencies at the front. But this is something that only theoretically happens. In practice, we can construct our own signals. So we can actually define what kind of signal do we want to transmit on that kind of conductor. So the front velocity is actually useless because I'm not interested in sending a very strong rectangular pulse, because there might be other use cases in which we can use a flat slope. And this is my personal opinion regarding the front velocity. So the conclusions, either this principle is limited to analog audio signals, and if so, what can we use that for? For example, for my passion, but maybe there are other applications I don't know yet. Or in terms of digital signals and worldwide digital networks, we have to find new ways how to deal with flat slopes. So it's more an engineering problem rather than a physical problem. I simply accept the physical background. I accept that there is superluminal transmission within certain frequency ranges. We just have to find ways how to actually make that work in terms of engineering. Okay, and there is a lot I want to do in the future, but these 5 aspects I would like to explain more in detail after we have presented our experiment here. And with that statement, I so far want to conclude my talk, and I'm looking forward to any questions.
Thank you for the presentation. I need a question on a concrete aspect to prevent misunderstandings with the audience, because this has been somewhat theoretical. Inside the guide, is there an empty space? Is there air? Is it medium? What is it? Could you describe the guide? Because still I do not understand your guide.
Oh, it's very, very simple. The guide is just a copper tube. So there is air inside.
So there is air.
Yeah.
And at the beginning there is a guide, there is the port.
Right.
So to my understanding, you have a port, because this is all theoretical. Okay, this is now concrete.
Wait, I think this, 1 second.
No,
here we go, here we go.
The other one, but it's not that clear.
So this is the conventional waveguide that is actually made for a normal microwave, which we send in a conventional way. And there is air inside, so this is a hole. It's a metal tube.
Okay, yeah? But in your particular description specifically, you have a special port for the injection of the electromagnetic wave.
What I do is, at one part of the experiment, I send the signal in a conventional way through this.
Unfortunately, I don't see the light bouncing unfortunately, but this is my difficulty. I think others too. That's why I use the stick. I use the stick because everybody
okay.
The pointer, unfortunately, this.
Okay, yeah, so the wave is inserted here into that hole.
What is there?
What is there?
What is there physically? You have a plate. In other words, we need a concrete engineering information on what is your guide. I will be very grateful if you do so.
This is a waveguide. This is usual in microwave.
Let him describe, because there are several.
Are you able to explain
guides.
it more descriptively than I did? Because
it should be clear for anyone.
There are many. No, I disagree dramatically. There are many different types, and the slightest change has major implications. No,
I'm not sure, but I guess it is made of copper or some other metal.
Are you part of the experiment or not?
I'm not part of the experiment.
But you made comments, so
you end up confused. Experiments, therefore I say I have not the slightest doubt in the result.
Yeah, but ask for please, everybody. Let's ask for your comment. I will be delighted to give you. But
okay, so no problem.
Otherwise, we end up in a disruption.
So we have a signal generator, and that signal generator generates microwave with approximately 9.15 gigahertz. So it's actually a vibrating sine. That is the carrier frequency, and this carrier frequency comes out of that cable, a microwave cable, which is able to carry the frequency of 9.15 gigahertz. And now, and this is maybe what your concern is about, we have we have to get that frequency onto the waveguide.
How do you do it?
And this is done via that adapter. This adapter is kind of an antenna, and this antenna, was heißt abstrahlen?
Irradiate.
Yeah, it irradiates that microwave from the cable into the copper waveguide. So this is the way how the wave is transformed from the cable towards the waveguide. Can you help me out? Just describe it a little bit better? I don't know.
Yes. It's transmitted to the rectangular waveguide because the rectangular waveguide has a low. The rectangular waveguide has the lowest attenuation, therefore, compared with the cables. And therefore, all the engineers are using the rectangular waveguide. And here you can see it later. And however, the rectangular waveguide is very expensive. A meter is about €100 or $1, and this is very cheap. And this is used for TV transmission to the satellite, this mode he has shown before.
Maybe one other comment.
Circular mode, they use exactly this adapter from rectangular to circular line to the satellite, 40,000 kilometers up. And
But we are at the entrance now. Could you describe what happened after?
okay,
Also, if you show it, it would be very nice for the
Sure.
audience, because we need concrete.
Of course,
yeah,
sure, no problem. So I just unplugged
The-
everything.
Thank you. If there are secrets...
this commercial
No.
copper
Because
has
this
a
was very
diameter
abstract. Both
inside of
presentations were very abstract.
2
We
centimeter.
need engineering
No
data.
problem, no
And
problem.
there's a barrier with 14 millimeter instead of 20 millimeters. That's our tunnel. And we put this on the beginning and on the end of the 50 meters.
a barrier?
This is a barrier, yes.
But there's a hole inside. Is that
Why it is a barrier?
Because it has only 14 millimeter diameter. That means it's a
Smaller?
It is smaller than the wave
Yes,
can
it's
travel
smaller.
through anymore. Yeah.
So there is
Yeah.
a hole here, so everybody should see that
So
it's
it's
a hole
smaller.
through the...
It's a barrier.
That's a barrier.
In what sense? Is
Like
it a barrier?
a-
Because there is a hole.
That's for this one.
But there is a hole, so it's not...
Yeah, that's
to be a barrier should be totally solid.
he has shown you the
Maybe a stupid question.
No, it's all right.
the
Yeah.
rectangle. Here you see the same. On top you see the narrowed,
Smaller.
the smaller one. This is also a barrier for long wavelengths cannot be transmitted in a small waveguide. The length should at least be given by half the wavelengths. Otherwise, you have a barrier. And this is very similar. It's exactly like the...
Like in a music box. If it is too small,
Yeah.
you cannot transmit the bass.
Wait, please identify yourself because you are on the mic.
I'm Professor Schmeichel from Vienna, mathematical physicist and sociologist, and we have done some experiments, and I've written a book about primordial space, and that shows why Feynman theory is incomplete, and that transforming this into the Clifford algebra, you get solutions.
Undersized waveguides, is that called? Undersized waveguides.
Undersized way.
We have all we call it.
Thank you for the overview. Thank you.
The dimension should be
No.
larger than half the wavelength. Otherwise,
No.
you have to cut off.
Now, a stupid question. Why that guide is not fully solid? It's only, so it's a partial barrier.
What did you say? Why is it?
By definition, a barrier is a wall with no hole. So, could you elaborate? Yes.
You always
In
like
in-
lithium or-
we are here at an engineering level, so no theory, please, no theory. So could you elaborate a little detail the function of the hole? Because I believe it's very important to understand your instrument.
We have a special mode in the rectangular, and here he has shown the picture. Can you show once more the transmission from the rectangular to the circular here?
Yeah, this is an important picture from an engineering viewpoint.
Here you see
Yes.
the adapter from rectangular to, on the other side we have the circular waveguide. And we did this just, but it's cheaper. And for the TV people, you can at the same time transmit two polarizations. The polarization is constant. It's connected to the spin of the photon. Therefore, it's conserving up to the yeah. It's the spin is stable up to the satellite, 40,000 kilometers away from us. So you can send. You can see the adapters two polarizations. That means you have double the channels.
So what does it have wavelengths?
Wait, let's
The
finish.
wavelengths here.
Let's finish the description.
This is the
First.
description.
So, yes, thank you. So, we start here, we have understood the guide, then what, could you describe, please, could you describe, sorry for very
No, it's all right. So again, I'm going more into the details. So we have the cable. So here we have the result. We have the carrier and the signal modulated on top. That goes into this adapter. And so you have to see it like that. The end of that cable works like an antenna. So it radiates the wave into the waveguide. So this is the waveguide that is able to transmit that frequency that I was just talking about. And if I directly put it here and I feed it back at the output, I would measure a transmission with the speed of light. This is the conventional way. But instead of that, we do something else. We use the undersized waveguide and place it here. So that means that everything that comes out of the adapter is not transmitted anymore. It is reflected. But that's not the whole story. 95 or 96% is reflected, and 4% is transmitted through the barrier. And this is the funny part. And after it is fed through this tunnel, there is no time delay between the input to that tunnel and the output at the end of the 20 meter. That's scary, but this is the way it is.
Thank you. Now, finally, I understood your guide, because concretely, because from the theories...
it's very interesting that the polarization of this one is the same of the two left-hand and right-hand circular solutions of the circular waveguide. You understand? So the polarization is still the same.
Yeah.
Any questions?
And do you know who has calculated all this stuff? 1944?
Richard Feynman.
Nine? Not. But he got the Nobel Prize together with Richard Feynman. It was Julian Schwinger. Julian Schwinger did all these calculations. At that time, he was a young postdoc at Alamos for the radar. Therefore, he was a specialist in differential equations.
Okay, let's go to the question, please.
I have a question. Is about the signal, right? You say it's have no time to propagate through the 20 meters guide, right? And it's not possible just the you just detect the signal is because they have a phase shift. So actually it takes time, but because the phase shift
you mentioned something that is important. And this is actually what most people use in order to attack the experiment. Most people say, well, this is just a time shift that is not related, no, this is just a phase shift, which is not related to a real time shift. And in certain engineering fields or in certain aspects, this is true. 1 second, please. Yeah. No. Here. If I use that a single pulse.
If you can point with your hand, because I don't see the...
If I use a single pulse like this gray one, it is very obvious. If that pulse is more shifted to the left, it is faster, and if it's shifted to the right, it is slower. So this is something where we cannot talk about phase shift. So this is a real time shift, obviously. But in case of a vibrating continuous sine, we might allow that kind of interpretation. I'm using the sine because it has a very, very small bandwidth. So this is the reason why I'm using that sine. So in that sense, I allow people to actually attack me. But I verified this principle with sine so often, and it is very obvious. Like if I use 20 meters, I have a time shift of 100 nanoseconds. But if I used only 10 meters, I have a time shift of 50 nanoseconds. If I have a distance of 50 meters, as we will show after the coffee break, I will have a distance of 200 nanoseconds. So this directly corresponds to that principle. And this is why I consider the usage of a continuous sine as valid. because it directly corresponds to the principle of actually shifting, of actually applying that principle.
Yes, thank you for the question. Just a moment. It's a very, very important question because it reflects the interpretation by the, the broader scientific community that we are talking about the phase velocity. But when the group velocity is insisted to carry a signal, then there is the claim of violation of causality, if interpreted as in empty space. If it is instead the system is interpreted as an interior problem, then the foundations, the definition of special relativity are inapplicable. Then you can defend yourself. But that's my personal viewpoint. Professor Animalou, there was a gentleman before you. You will be next. You will be next.
Paul Laviolette. I would say the pulse is not instantaneous, it's just very fast. It's just you can't measure the speed. I mean, it could be going a million C in there.
It's actually delayed by 120 picoseconds.
Oh, so you do see a slight...
There is a scattering delay at the beginning of the barrier, and that corresponds to one wavelength. And this is with 9.15 gigahertz corresponding to 120 picoseconds.
Okay, so if you doubled the length of your pipe, would that double also?
No. It's a universal scattering time at the beginning of the tunnel.
It's very possible you're up at millions of C. I've been working on the superluminal propagation for the last 10 years. We did an experiment with Gaio Belansky 8 years ago, where we sent superluminal shock fronts across the laboratory, 3.5 meters, beginning at around 6 C, and diminishing because of the geometry. It was a 1/r drop-off of the extra speed. And I have developed a theory of how this happens, which can explain that this is not really so spooky. And to understand this, you have to understand that photons have longitudinal components. And what you're doing with your restriction is you're kind of stripping off the transverse part of the photon, leaving the longitudinal component. And longitudinal waves, which Tesla was working with, can travel superluminally. And it depends, the speed depends on the gradient of the front. So if you're working at fairly high frequency, so your pulse will have a fairly sharp gradient. And to understand why it's superluminal, you have to understand that there's an ether. So this is proof of the ether, because what is happening, you have an electric field gradient in the front of your pulse. It's propelling the ether, because you're creating an ether wind in the pipe, and your pulse is surfing the ether wind. And the sharper the gradient, the faster the ether wind, the faster your pulse goes. This also ties in with Podklanov's work. You know Eugene Podklanov with his gravity impulse beam? Do you know that he's measured with his first setup, he measured 64 C. His beam is undiminished over many kilometers. He's been able to knock over books in a library 2 kilometers away with it. He's developed a more intense pulse. It goes to 10 megavolt discharge, where he's put holes through concrete blocks, also bent to steel plates. He's confided to me that he's gotten several thousand C minimum, because it was beyond resolution. He used atomic clocks to measure the speed. There again, he's working with a longitudinal pulse. So all of these things tie together, and I think we can come up with an explanation. And maybe you should also consider the shock front approach as another means. Like Podklanov's beam is a very easy way to go across continents because it goes right through matter. It's a gravity beam. So there's no real, he's done an experiment where he's gone over 100 kilometers and detected effects with this. It's phenomenal. I mean, it breaks all the laws. It stretches the imagination. We're talking about superluminal propulsion for spaceships here, if you want to apply what Pakhanov has. And he's ready to go forward. He just needs money.
As anybody in that field, right? Yeah.
Yes, thank you for the beautiful comments. They do make sense.
I have the data with me if you're interested.
Yes, I'm interested. I would like to make a comment, however, that not necessarily no question about with the longitudinal impulse or wave, you have arbitrary speed, essentially arbitrary speed. But there is one point I would like to clarify. There is the alternative, one alternative, what you said, namely that they strip the transversal part and only longitudinal goes through. But there is also the other possibility that the longitudinal impulse is created by the barrier. And because the normal electromagnetic waves are Maxwell equation, Maxwell has no longitudinal solution. Yes, it's a possibility in which I'm myself work. The eterino that we discussed, the notion of the eterino, the energy that is needed for the synthesis of the neutron, is not necessarily longitudinal and has an arbitrary speed. The wave of that eterino, the wavelength of the eterino is about, as was asked yesterday, is the size of a galaxy. So basically, you have with longitudinal impulse, you have arbitrary speed.
Also, this ties in with quantum interconnectedness, by the way. In subquantum kinetics, I can say this in the talk I'll do. I propose that there's soliton connections between nucleons that come into close contact. And even at separated great distances, the soliton beam is still there. And basically, the connection is longitudinal. They're basically soliton being formed by longitudinal waves.
Yeah, that's okay. Thank you.
My name is Alex. My question is, when you transmit square wave, you get into circular wave, right?
Yes.
To your waveguide. Now, is it reversible? That is, can you go backwards and go from the circular wave to the square wave?
Yeah, that's...
Is it perfectly reversible?
Yeah, it's and at the beginning of the waveguide, because of that adapter, because that's the reason why we use that tube. It is, well, it's cheaper. This is why we use the adapter. We can't use a 50-meter rectangular waveguide. We actually don't get it. But what we get is the circular one. This is why we have the adapter. We feed it into it. We have the rectangular. We have the circular. So this is where the transformation is happening. And at the end, we have the transformation back from circular to rectangular, and then to the cable.
Okay. Now, I'll tell you now how we convert. I mean, the experiment we do, I entertain people who visit my office. If you have a Nokia phone, it has numbers 1 to 9 arranged in a square, right? That is called the magic square. Then you give me, and instead of transmitting the name by pressing zero like live, I transmit the integers. Then I add the integers, and I give you the geometry. That's the number of lines, points, and planes that corresponds to that. This is of interest because a student working in cubic arts, that is, we can convert every person to a cube or some form of, an image of the person will appear. So this is the way we do it with the phone, just an entertainment. Thank you. So I wanted to know if it were reversible because in the Lie admissible approach, it should not be perfectly reversible.
Mm-hmm.
Thank you, Professor Himalu. Yes.
So you have mentioned a problem regarding the bandwidth. Is it possible to use this device for multiple times?
That is something I will
F,
cover in the future work,
yes,
right?
Because it is you can use the same waveguide for several frequencies at once. Because if they are not interfering or make an obstacle to each other, you can use the same 15 meters of guide for maybe 5 generators at once. 5 different generators at different frequencies, and send
But the problem is that you have
and organize
to
a
build
barrier for 5 times at once.
We have always
Is it possible?
special bandwidth for each waveguide, bandwidth of 1 octave only. Otherwise, you have higher modes. Therefore, the engineers using this only, let's say, from 8 to 12 gigahertz, this one, this size. And if you have a longer wavelength, a lower frequency, then you have to use larger diameter, cross sections, and so on. And
So you
in
see
the opposite.
It's not possible to say.
No. We can measure only between 8 and 12 gigahertz. Otherwise, we have higher modes.
Any other question, please? If I don't see you, I apologize. Any other question? Well,
You want to have it zero.
how-